Okay, today I was going to talk a little bit about the solutions to homework 4. You guys did the model building and model selection routine, and I'm sure you noticed that there were many choices that you could have wound up doing. Lots of different choices of models. And so I just wanted to talk through that a little bit, about that process of choosing a model. I'll show my solutions, and before we do that, I posted a couple of articles on eCampus this morning. So under course content, there's now a folder called articles, and there's 2 papers in here that are relevant to this issue. Let me download these. The first one, called Model Selection, is from a criminology background. So it's not exactly a relevant application area to what we've been doing, but the topic is relevant. Bless you. So let me just pick a few sentences out of the paper to discuss with us here. The abstract: conventional statistical inference requires that a model of how the data were generated be known before the data are analyzed. As in, if we're going to conduct an experiment, collect data, and use the data to answer a scientific question, the way the statistical machinery is designed to work requires that the model is known before we get started. So the ideal situation for using hypothesis tests and confidence intervals to answer scientific questions, the ideal is that we write the model down before we even see data. Clinical trials, for example, where we need to be very rigorous and careful in the way that we assign statistical significance, would require that you say, I'm going to collect this many people, I'm going to do these treatments, I'm going to measure these variables, and the model I'm going to use to answer this null hypothesis question is such and such. To say that, you have to know things before you collect the data. I know these variables are important. Sex, age, race, those types of things are critical components of describing a subject. And so again, ideally, you write that model down and you say, here's the coefficient or the coefficients that answer the question of interest. I'm going to adjust for these variables because of such and such and so and so. Here's why I think we need to adjust for these things. And I don't even have to show you data to argue for it, ideally. Published literature has shown that there are gender differences between these types of things. So as much as possible, saying, here's my model and here's why, without even seeing the data. Once you've written down the model, then in terms of the coefficients of the model, you can characterize what you're trying to do inference on. Treatment effect boils down to this coefficient, so I'm going to test at significance level alpha equal whatever by looking at this coefficient. The problem is when we collect the data and we then use the data to aggressively pick the model. So we've seen a little bit of that in practice this semester. So let me just see a couple of things that they say about it. In criminology, that's where these folks come from. Social sciences more broadly, really anywhere that you go to look where people are doing statistical modeling and doing inference. This model selection, model building routine shows up an awful lot. And it's not often questioned in the literature. So you will be ahead of the curve a little bit if you're thinking in these terms of, I want a model, and as much as possible, I want to decide on that model without using p-values and stuff to choose it. So in many applications, a variety of model selection procedures are usually or are routinely undertaken, followed by inference on a, quote, final model. That is the issue that we're kind of worried about. So they say, when we do that, there's many ways that there can be problems. I showed you a simulation earlier this semester with the stepwise model building algorithm, and we just looked at what happened. Confidence interval coverage, for example, was destroyed. What we called 95% confidence intervals in the simulation routine or scenario were nowhere near having 95% coverage. So how that happens can be from complicated mechanisms. For example, the parameters being estimated are no longer well defined. If you're going to collect data and estimate a parameter, you need to define what the parameter is before you go out and collect your data and estimate it. For example, the treatment effect coefficient in a regression model, the exact interpretation of that coefficient depends on what else is in the model. So do you mean the treatment effect holding gender and race and age constant? Or do you mean treatment effect holding something else constant? Ideally, you write down the exact parameter that you're going to be working with. The sampling distributions of the parameter or parameters of interest after doing model selection are not what we claim that they are. They are more complicated. They are functions of everything that happened leading up to the choice of the model. So that can make the properties of our inference be very different from what we think they are. So this is kind of a long paper, 31 pages. I'll let you browse through it on your own for the most part. But they go through and talk about this issue in the context of logistic regression especially. But the implications are for any regression model. Any model that we use data to decide on it, there's this challenge, potential issue. The other paper that's here is called p-hacking. Maybe you've heard that phrase. So there's an issue in science generally that you're more likely to get a paper published if there's a statistically significant result. If you have a paper, you spent thousands of dollars, did this experiment, you did your data analysis, treatment effect is not statistically significant, there is demonstrable evidence that that kind of result is less likely to get published. For one reason or another, whether people are doing it intentionally or subconsciously, reviewers tend to shoot down papers that don't have an interesting result or quote interesting result. What that can result in is, and I've experienced this several times collaborating with people across campus, what that can result in is, well, we did our ANOVA model or our regression model, and we didn't quite get statistical significance of the variable that we were interested in. But we're pretty sure that there's an effect. I mean, we can see it. Other people have had papers that showed it. Look at this one mouse that's in our data set. It looks maybe like an outlier, and if I remove it, the p-value goes down to below 0.05. Let's try 30 different models until the p-value gets small enough. Happens a lot. And you can understand why it happens, because it's kind of a subtle issue, and unless you've had, a fair amount of statistical training, you may not even be aware that it is an issue. This phrase, p-hacking, refers to taking your data and hacking it, manipulating it, looking at it from every different angle until you get the p-value you want. And that is definitely a problem because of this issue and the simulation that we saw. So just imagine, of all the papers that have been published, all the papers in different application areas, maybe they were written by people who are not statisticians, or there wasn't a statistician on the research team. Wonder what proportion of them have unreliable inference because of this p-hacking thing. Happens a lot. Okay, so a focus on novel, confirmatory, and statistically significant results leads to bias in publication. There's something called publication bias, which is, and let me just say something about that publication bias briefly. It's unfortunate because suppose you do an experiment and you're looking at the effect of some intervention, a diet or something, and you get an insignificant p-value. Arguably, that's just as valuable a contribution to the research community as a statistically significant finding. Because if you publish your result, this particular diet applied to this population of mice under these conditions did not make a difference. What that is, the value in that is that you prevent other people from wasting their time and resources and looking at the same question. So if your negative findings don't wind up in the literature, then the potential is for it to be repeated, and we don't actually learn. A negative finding is something that gives us new information. We know what does not work. The idea of p-hacking is what I was describing earlier, where we have data. We want this p-value for the diet effect to be small, so we're going to try every last thing we can do to make it be small. We could try transforming the variables. Should we log transform them? Can try, obviously, which covariates to put in the model and which to not put in the model. We could try different assumptions of the model. Really just an endless choice of ways to do this. These guys and gals come up with a result that suggests that the p-hacking is maybe not as bad as we fear. So they have some simulation results and real-world results that say when there are real effect sizes, we will tend to find them even if we do this p-hacking. The challenge, I think, is more about when there is not a statistically significant result. Because the harder you look for one, the more likely you are to find one by trying lots of different models. So they paint a somewhat rosier picture. suggesting that p-hacking probably does not drastically alter scientific consensuses drawn from meta-analyses, at least. We haven't talked about a meta-analysis. Let me just define that term briefly. When multiple studies have been done of a particular problem, maybe there's 10 published papers. They were all relatively small sample sizes. We had 30 mice. We did this study on this particular intervention. Somebody else did a study with 20 mice and on the same intervention. When there are repeated studies, what would be great is if you could take those 10 small sample size studies and kind of fold them together into a bigger sample size study. If 10 different labs did essentially the same experiment with 20 observations, can we not put those all together into basically one study with a big sample size of 200? Meta-analysis is a statistical technique for doing that, or attempting to do that. It's a simple idea, but it's a fairly complicated thing to do in practice because of all the variables that exist from one study to another. This person's study was done at this lab with these specific conditions, these specific characteristics of the population, maybe slightly different protocols that were used in the laboratory, maybe slightly different qualities of the study design. So what a meta-analysis tries to do is like a weighted average kind of combination of multiple studies. Let's upweight the studies that were higher quality, maybe that accounted for more potential confounders, and so we have more faith in these types of studies that they were done in a way that's reproducible. And other studies with lower quality, like maybe they didn't adjust for many, if any, covariates, weight those lower in the overall assessment. But meta-analysis at the end of the day takes multiple studies and boils them down to a single consensus. In terms of value of different types of claimed results from statistical analysis, there's a wide variety of how strongly you should believe the claims, ranging from anecdotal findings that you have really no reason to put much faith in, to randomized, double-blind trials with lots of good informative covariates adjusted for. If we have time, I do plan to talk a little bit about different types of studies that can give rise to data and claims, and how we can evaluate them, how convincing is the results, the claimed results of a study, based on how the study was done, what they measured and what they didn't measure, sample size, things like that. Okay, so anyway, you've got a couple of papers that you can look into that speak to this issue. But p-hacking is another descriptive term used for this issue. I want to look at the solutions and talk about the issue in the context of the two data sets you guys played with. Here are the solutions. Did anybody have any questions or concerns about the first one? I think that one was, yeah? So number one was the survival curves. Okay. I think the first one, I think we were, based on my feedback from others, I think we were okay with the first one. So let's consider the two that we did actual model selection for. Let me see if I can get all my code out of here. Here is my code for the lung data. Lots of code. Okay, let's work our way through this and talk about it. I need to library survival. And so I recoded status. We talked about this in the Q&A, I think. Status, changing it to be 0, 1, consistent with the parameterization we've been using. And I did this recategorization of the physician.ecog variable. Remember, it only took, I think, 0, 1, 2, and 3 as the values in the data set. Those were the only 4 values we had. But for the equal to 3 category, there was only 1 individual in that category. If we wanted to treat that variable as numeric, it's not an issue. It doesn't matter if there's only 1 instance of one particular value. That's not a problem. I decided to treat ph.ecog as categorical, and having really low counts for 1 or more of the levels can be problematic in that context. So I decided to recode the 3 group to a 2 group, and then I was going to treat gender and the ph.ecog variable as categorical. So setting them up to be factors. Okay, then we looked at one at a time. Let's consider each of these variables one at a time. With a categorical variable, simple way to do that is to look at survival curves, and both of the gender and ph.ecog variables were pretty clearly associated with survival time. For the quantitative variables, all of them except for meal calories and weight loss were statistically significantly related to risk. So I decided to remove those 2 variables. Here you could argue, what's our sample size here? Dim, long, 228. We have 228 observations, and 1, 2, 3, 4, 5, 6, 7 covariates, variables. So let me say something general about starting out with the model selection process here. Somebody decided, the PI of the study decided to measure these variables. There is reasoning behind these variables that were measured. So, from the get-go, I would prefer not to remove variables. If the variables that were provided to me were selected with good rationale behind them by the PI, I would prefer to leave them in the model. especially given that we have a pretty big sample size that can be spread across these variables, 7 variables, in such a way, there's roughly 70 observations that can be set aside for, not 70, 30 observations that can be set aside for each of the 7 variables. Which to me says we have a, quote, large sample size for accommodating all these variables. If you remember back to Stats 101, where we said there's this central limit theorem, that if you want to do inference on a mean, one mean, if you have, the rule of thumb is 30, at least 30 observations, then that's a, quote, large sample size, and large sample results can be applied. The sample mean is approximately normal, for example, as long as you have a, quote, large sample size. A similar kind of dynamic happens with regression models. To the extent that you have a large sample size, the inference that you'll get out of the regression model is reliable. The p-values that are next to the coefficients in the regression model are large sample-based p-values. So if I have a sufficient sample size to accommodate a model, and the variables were there from the get-go for defensible reasons, I would prefer ideally to not remove any. That said, we did have that these 2 variables were not contributing much, apparently. So following the routine that we saw in the textbook, we could propose removing them. Let's follow through the routine that we've seen, and then I'm going to go back and consider what happens if we didn't do this. Because one thing to consider is if we're worried about the model selection routine and any impacts it's going to have on inference, one thing to consider is how sensitive is the final model to just what we put in as the model. There's a technique in modeling called sensitivity analysis. If you come up with a model and you have a p-value for the relationship of interest, a question that's good to ask is, what if I removed 1 or 2 of the variables? Or what if I didn't remove a couple of the variables that I did? How sensitive is my final result to those choices? Ideally, it's not very sensitive. You would like to be able to show, here's a reasonable model, gives me this conclusion, this statistical significance, and there's a little bit of plus or minus that can be accommodated. If you were to change the model slightly, it does not change that much on the final conclusions. So I want to look at that with these data. We're going to initially remove meal calories and weight loss. I think everybody did that because the p-values were really big for both of them. Here's weight loss, p-values 0.8. Here is meal calories, p-value 0.6. So I'm going to start with this multivariate model that has everything but those 2 covariates. Here's what the output looked like. We have marginal significance, well, really not significance for age, as well as the 2 Carnot variables. So when we come to the step of considering removal of covariates, those would be the ones we would consider, age and these 2. If we're going to do this game of considering removing variables, ideally we would do it one at a time. Let's consider age. remove it, what happens? Then let's consider ph.carnot, what happens, and pat.carnot. That would be ideal, because then you'd be able to see every one of them one at a time. I cheated a little bit and considered all three of them together. Really, the reason I considered all three of them together, to be honest, was that I was not real eager to remove more variables. Didn't have that many to begin with. There were only 7. We already got rid of 2. These 3 have, they're reasonably close to being statistically significant. So I'm not eager to get rid of any of those. I considered all 3 of them together. Considering all 3 of them together will probably result in some differences. pH.ecog1, for example, that coefficient for comparing ecog1 to ecog0 went from 0.59 down to 0.42, and the second one went from 1.09 down to 0.96. In terms of deciding, is that a big difference or not, I would recommend thinking about it in a couple of ways. One way is what is just the raw difference in these coefficients? Going from 0.59 down to 0.42. What difference is that? We could ask 0.59 minus 0.42, and what percentage of the 0.59 is that? The change in the pH.ecog1 coefficient is nearly 30%. So something over 20% is, I think, a reasonable rule of thumb for calling it a substantial raw difference. What you, I think, ideally would also do, though, is ask how much of a standard difference is that. So remember that you can have a difference of 30% between two numbers, but if the estimates that you're looking at, if the estimator that you're looking at has really big variability, if its sampling distribution is really spread out, then maybe 20 or 30% is not unusual. Maybe it's not something that would be what you would call significant. So what you could also do, in addition to looking at that percentage change, is you could ask how many standard errors away from the original one is the new one. The standard error, standard deviation of this coefficient is about 0.24. So how many standard deviation units away is this 0.42? Let's do 0.59 minus 0.42 divided by the standard error, 0.24. How many standard deviations away from that original estimate is the new estimate? It was 30% on a raw scale, and it was 0.7 standard deviations away. In terms of saying that, yes, there is a difference with and without this coefficient, ideally there would be a, say a 0.5 or 0.75 at least difference in standard deviations, and a substantial raw difference or percentage difference. The reason I say both is because the raw difference, like I said a moment ago, could be 30%, but it could be a very small number of standard deviations. If the standard error were much bigger, like 1.24, that's a 30% difference, but it's only 0.14 standard deviations away. So not really distinguishable from random variation. And going the other way, a 0.5 or greater standard deviation difference, I wouldn't arguably care about it if the raw difference was inconsequential. I mentioned earlier in this semester the study from 15, 20 years ago where I think it was called the Nurses' Health Study, a big observational study that was looking at the use of hormone replacement therapy for postmenopausal women. And they found a statistically significant increase in, I think, breast cancer risk for the women who were on hormone replacement therapy. And so the study was stopped, and many people went off of their hormone replacement therapy. If you're on hormone replacement therapy, your probability of getting breast cancer increases statistically significantly. P is less than 0.05. But the actual raw increase was arguably not big enough to even care about. So, for example, maybe it went from 1 in 1,000 to 2 in 1,000. That's a 100% increase, and maybe it's statistically significant. But the actual implication to you as an individual is a 1 in 1,000 increase in your risk. So if the risk is really small to begin with, arguably a doubling of that risk is not something to be all that concerned about, especially in light of the other benefits that the therapy might bring to you. If you're postmenopausal, you can get very uncomfortable, you get overheated and can't sleep, that type of thing. So maybe it's worth it. That's difference between statistical significance and practical significance. There are differences. So I would recommend looking at the percentage change and also the number of standard deviation differences in terms of gauging whether things actually changed. In this case, I would say the coefficient for pH.ecog, at least that first coefficient, changed substantially. I think what I have here, I didn't treat, let me see. I think that's the wrong percentage. I think it changed by about 30%, which was about 7 or 0.7 standard deviations away. So when I pulled out all three of those marginal covariates, age, pH.Carnot, and Pat.Carnot, there was at least one what I would call substantial difference in the resulting coefficients. So remember, we care about changes in the coefficients when you pull out a variable because that is potentially indicative of confounding. On that topic, let me say something else that I haven't told you guys yet. If we have a regression model, like let's say y is equal to beta 0 plus beta 1 x, beta 2, let's call beta 2 treatment. So we'll say treatment is either 0 or 1. 0 is control, 1 is treatment. And our interest is in that coefficient. Is there a treatment effect? Let's do inference on beta 2. We have this other variable x. And we can characterize this other variable into one of two categories. Either a confounding variable, in which case it needs to be in the model. A confounding variable is one that without adjusting for it can result in incorrect estimates. It needs to be adjusted for, or your relationship of interest will be muddied, confounded. So a confounding variable, one that without it, the coefficients for the other variables in the model change substantially, needs to be adjusted for. You don't consider removing those because they are necessary to get unbiased assessments of the treatment effect in this case. If it is not a confounding variable, if the coefficients of the other variables do not depend on it being in the model or not, we can call it a precision variable. What that means is it's not necessary that you adjust for it. You don't have to adjust for a precision variable because it doesn't affect the other coefficients. But a precision variable, you may want to adjust for it because what it does do is increase the amount of variability that's being explained, which will result in decreased standard errors for the other coefficients, which is equivalent to increased power for the other coefficients. So suppose we're doing treatment and control, and X is age, say. Suppose the treatment effect does not depend on age. Age doesn't have to be in the model. We can get an unbiased estimate of the treatment effect even without it in the model. But by including age, we explain more of the variability in the data. That will translate to a lower standard error for beta 2, which will translate to increased power for beta 2. If you think about what we do when we do a test, for example, a t-test looks like estimate minus null value divided by standard error of estimate. If we can decrease the standard error, the denominator, the test statistic gets more extreme, gets bigger. And bigger test statistics correspond to smaller p-values, which is higher power. In terms of characterizing the variables in your model, think of it in terms of, is this a confounder or is it a precision variable? If it's a confounder, it needs to be in the model. If it's a precision variable, we can make a decision. Why would you ever not want to include a variable? Suppose that X is, we think, a precision variable. Why would I choose not to include it? Well, suppose we had a sample size of 300 and we have 150 covariates. That essentially is a small sample size problem. Think about how many observations do you have per variable. Don't have many. So in cases where sample size is at a premium, you might not want to include a precision variable. If you have plenty of observations to go around, you really have no reason not to include a precision variable. Okay, confounders, precision variables. Here we have evidence that age, pH-Carnot, and pat.Carnot, at least one of them is a confounding variable because the coefficients for at least one of the remaining ones changed. So I'm going to keep all of them in the model at this point. The only thing that's been removed is meal calories and weight loss. Then we can, using graphical techniques, say we can investigate the, quote, functional form of the remaining covariates. If it's a categorical variable, there's nothing to check because you don't make really any assumptions by saying there's a different mean for every level of the categorical variable. But for the numerical variables, we have to think about, is it a linear relationship between log hazard and that variable or something else? Is it quadratic or what? So I have these pictures that roughly look at the functional form. ph.carno, when I binned that variable and looked at estimates by bin, looking at these estimates, they look roughly linear. That looks pretty linear to me. Pat.carno looked pretty linear. Let's do that. Looks pretty linear. But age looked decisively not linear. So I still have age in my model. You may have decided to remove it, which is fine. As long as you give reasoning behind what you did, I'm happy with it. So here was the picture with age. Pretty clearly not linear, which says I'm not comfortable putting age in the model as just age. If we were doing linear regression, not Cox proportional hazards, we could make this type of picture more easily. We wouldn't have to do this binning. We could just make a scatter plot of response versus age. The reason we're doing these specialized pictures is because we're in a Cox model setting, and it's a little more complicated to, I can't just compute the hazard function, for example. But this picture here suggests to me that linear is not sufficient for capturing the essence of age. Let me say something about that real quick. Maybe we don't care so much. If age is not the variable of primary interest, then all I really want to do with it is adjust for it. I want to adjust for age. And in some settings, if sample size is at a premium, you don't have enough samples to fit a sophisticated curvy model, say, you could arguably leave it as linear and just acknowledge I probably didn't get it fully characterized, but if the goal is only to roughly adjust for it so that we can make valid inference on another variable, I've seen people do that. That doesn't look linear, but I'll go ahead and treat it as linear since all I'm doing is adjusting for it. I think the ideal thing to do is to make your model be flexible enough to accommodate this apparent nonlinearity. So that's what I'm going to do in my solution here. Down below, here is my current model. Meal calories and weight loss are gone. Everything else is in there. The only change that we've made to the preliminary or initial multivariate model is to allow age to be squared. FYI, if you want to include age and age squared in the model, R will not do what you want what you think it's going to do if you were to do it like this. If we did age plus age squared, that's not the syntax that R wants. If I do that, even though it seems like that should work, what we end up with, there's no age squared term in there. So it does not recognize arithmetic in a formula. R does not recognize arithmetic in a formula. If you want to do a transformation of a variable inside the formula, what you can do is wrap it inside this capital I function, which basically means evaluate what's inside and use the result of that. It's not the most intuitive component of R's syntax. Another way you could do the same thing without messing with that I function is we could say age squared is age squared, and then reference that in here. Would do the same thing. But I'm going to include age and age squared. So we have, we're out of time, man. Age and now age squared. We have both of them. So I'll come back, I'll spend a little bit more time on this on Wednesday because I think it's a good discussion topic. It happens in every application of statistics, every experiment, every study. Somebody has to decide on a model. And what I want to show for sure is what I called sensitivity analysis. So let's, at the end of this script, let's go back and consider, suppose we made a different choice. What if we didn't include age in these other variables? At the end of the day, how sensitive is the model to those choices? We'll look at that. All right. So we'll pick up on Wednesday. Okay, thanks.